Hey everyone, this is Mr. Kramer. I'm just going to do a video going over the introduction for the next topic for this week, which is solutions. So this is the beginning of quarter 4. Every week we're going to have a new set of videos, a new set of assignments that will be posted on Monday, and then the material will be due at the end of that week, and then we'll start over every week. So this is week 1, and we're focusing on an introduction to solutions. So what I have you guys looking at here is an old graphic organizer that we used for understanding the different types of matter. So if matter is sort of the umbrella concept, everything has matter, all particles, atoms, desks, people. That's split into 2 categories. So those things that are pure substances, meaning that are totally one thing, versus mixtures. For solutions, we're interested in mixtures, particularly homogeneous mixtures, which are those where the small particles are dissolved so evenly and homogeneously or smoothly throughout that they can't be separated. And that's in contrast to heterogeneous mixtures, which is a non-uniform composition where it isn't well mixed, or more in our everyday speech we say that whatever the substance is hasn't dissolved. So I have reorganized this. I wanted to show this because this has all the definitions that we give, but I wanted to show this graphic organizer because I think it's just a little more clear because it doesn't have as many words on it. So if this big yellow shape is all matter and encompasses or encapsulates all possible matter, there's 2 main categories. So you have the pure the pure states of matter over here, and then all of the mixtures fall into this category. So those pure possible states of matter include elements or compounds, elements being just one kind of atom, compounds being maybe more than one kind of atom mixed together, but still a pure substance. Whereas over here in mixture, you'll see there's also 2 main categories. And the category that we care the most about is this one here, solutions, which we call homogeneous mixtures. And that's when everything is dissolved into a solution. A heterogeneous solution has 2 sort of types, so you got suspensions and colloids, but really these are all examples of situations where whatever you were trying to dissolve didn't dissolve. And so it was insoluble in solution, and it results in either a suspension or a colloid. If whatever you're dissolving does dissolve, and all of it dissolves, then we call it a solution. But if it doesn't, it's a heterogeneous mixture, more broadly, or as we just say in our everyday language, it didn't dissolve. Okay, so I have some examples of some stuff that does dissolve and doesn't dissolve. So for example, if I put cereal and milk, or ice and soda, it's almost silly to think of those things dissolving because we know they don't. In fact, on purpose, we don't want them to. But these are both examples of heterogeneous mixtures. Also, just like there are heterogeneous mixtures in phases that aren't liquids, but we're focused on liquids. So an example of things that are dissolved is, say, if I dissolve some salt in water, if I dissolve alcohol in water, those are examples of solutions. Specifically aqueous solutions. And so I'll write that word there, aqueous. Aqueous solution just means that it is in water. And that is going to be the primary focus for us for this unit, is aqueous solutions. So salt water is a great example. Any kind of alcohol, in this case vodka, is a great example of an aqueous solution. Okay. So before we move on, I want to cover a few main definitions. And so I want to go over these now just in detail so that we have them down. And then we'll watch a short video that explains or shows the process of things dissolving. So the first things first, what do I mean by solution? Well, we just talked about that it's a homogeneous mixture. And what that means is that everywhere you go inside this mixture, everything is evenly distributed, evenly spread out. There's no chunks or clumps or lumps. Everything is well dissolved. And so a couple of definitions in a solution. The thing that you're adding stuff to, that's the solvent. So in this case, for most of what we're going to be doing, this is going to be water. And the water is going to be our solvent. Sometimes it's called the universal solvent because it's just so common. We use it as a solvent in our everyday lives. We use it as a solvent in chemistry. So that's the solvent, whatever it is that we're adding stuff to. And then whatever it is that we are adding, whatever we're trying to get dissolved, is called the solute. So the solvent is the water. The solute is whatever it is that we're adding. And then together, those two things make a solution. Does that make sense? The next couple things just describe some more vocabulary. So I've used this word dissolve a few times, and that's what we're going to look at next in this video. So when the solute separates from itself and interacts with the solvent to form a solution, meaning I got a chunk of something that I've added into a solution, and it's going to break apart into tinier pieces. And I don't just mean kind of small, I mean as small as molecules and atoms, very, very small. And so that process of breaking off the different atoms as they go into the solvent, or the water in our case, that's called dissolving. And you've seen this before. And then these two words here kind of go hand in hand. Anything that's soluble, that means that it can be dissolved in water, or in a solvent. We're talking about water most of the time. And if it's insoluble, then it can't be dissolved in water. So if it is soluble, it can dissolve in our solvent to form a solution. So that's how those words sort of play together. Okay, so next we're going to watch a video that shows this dissolving process. Okay, welcome back. So what I have here is a video that shows the process of how water dissolves salt. So you've seen this process from the macro scale, where you have a cup of water and you add a little bit of salt to it and you stir it up, or sugar. It looks very similar. You stir it up, and the little particles kind of move around and they slowly disappear. Maybe the water gets murky for a second, but then it clears up, and then suddenly there's no salt left. So when we see it happening at a molecular level, there's a lot more going on, and that's what I want to try to highlight today. And in fact, it has a lot to do with the polarity of water, which we just spent a couple of weeks learning about. So if this is our water molecule floating around, all of those things in the background are also water molecules. Here it is coming face to face with a giant crystal of salt that's got this pink and yellow checkerboard pattern. So remember that salt is an ionic compound. So it's got sodium ions that have a positive charge, and it's got chlorine ions that have a negative charge, or chloride ions that have a negative charge. So this water, this is right after I drop a huge crystal of salt in there. What's going to help the water do its job is the fact that it's polar. So here, this big atom, that's the oxygen in blue, and that's got a slightly negative charge. And those two hydrogen atoms right there, well, they're in red and they have a positive charge. So this positive will attract anything that's negative, and this negative will attract anything that's positive. So you might be thinking, wait a minute, I know about positive and negative charge. That has to do with ionic compounds. So ionic compounds also have these positive and negative charges. The sodium ion is positive and the chloride ion is negative. So you can imagine that as this chunk of salt gets dropped into some water, those water molecules, the sides of them that are, let's see which one happens first. The sides that are positive, they're going to gang up on this negative chloride ion. A bunch of them are going to come in there and be like, hey, I'm attracted to you. I'm going to pull you out of this checkerboard pattern. I don't care that it looks pretty. What I care about is stabilizing my charges. So these water molecules, their positive ends are going to rip that negative chloride out of there, and the sodium doesn't get away with it. It's not just the negative ions that get attacked. The positive ions get attacked too, but from the opposite side of the water molecule. So this poor sodium ion right here has got a positive charge. We know that's going to attract the negative side of the water. So you're going to see the oxygen side, where the blue parts are, coming in and ripping that sodium ion out of solution. So this is called solvating, is another word that we use for this. But you'll notice that here we have a negative chloride ion. It's not labeled, but that's the chloride ion that's negative, and all the red bits are the parts that are touching it. And they're just surrounding it. They're just ganging up on it. And then similarly, for the sodium ion that's positive, all the blue sides of the water are ganging up on it. And so, as you can see, since I have so many water molecules, look how many water molecules are in the background there, I have plenty of them to come in and rip these different ions off of the salt crystal. So it's not just that the salt crystal is getting broken up, or it's melting, or something like that. Instead, it is systematically, piece by piece, getting ripped apart by these water molecules and then sort of isolated in these little water bubbles. And so you see the process can happen really fast. Look at that. Look how many water molecules are getting in there and ripping apart those molecules, ripping apart those ions. And so that's generally how the dissolving process works. Generally, you have a positive ion or a negative ion that's sitting in solution, and the water, because it's polar and it has a positive and negative end, it'll go in there and pull them apart. So we're going to look a little bit more at a demonstration coming up that Mr. Ellingson's going to do that shows examples of things dissolving and not dissolving, and then we'll try to connect it back to our ideas of polarity. Okay, thanks for watching.